Hello everyone, today I'm going to show you the brightest light-emitting chemical reaction, the interaction of dinitrophenyl oxalate with hydrogen peroxide in the presence of a fluorescent dye. And that's no exaggeration. Peroxyoxalate chemiluminescence significantly surpasses all other types of chemiluminescence in both brightness and duration of glow. This isn't luminol, this is much brighter. This very reaction is used in commercial glow sticks that can glow for hours. While the reaction in this video will be brief, it will be incredibly bright. This is dinitrophenyl oxalate, an ester of oxalic acid and dinitrophenol. This substance is the driving force of the reaction. In one of my next videos, I'll show you how to synthesize it. It's not difficult, of course, if you work in a lab. If not, you might encounter some challenges. Try to find oxalyl chloride to start. I specifically synthesized the dinitrophenyl ester because it reacts the fastest, producing the brightest glow, although it's quite short-lived. In my opinion, for demonstrating chemiluminescence, the brighter the better, because if you want it to glow dimly for hours, you don't need to bother with synthesis. You can just buy a glow stick. To observe chemiluminescence, another critically necessary component is a fluorescent dye. I chose Rhodamine 6G, which is quite accessible and inexpensive. The mechanism of the reaction is as follows. First, dinitrophenyl oxalate reacts with hydrogen peroxide to form a molecule called oxatenedione. It's unstable and really wants to decompose, but it can't do so until it sheds its excess energy. It sheds this energy to a fluorescent dye molecule when it encounters it. The oxatenedione then calmly decomposes into two carbon dioxide molecules, while the fluorescent dye transitions to an excited state. Afterward, the dye returns from the excited state to its ground state, releasing a quantum of light. This is the light we see, and the color of the light completely depends on the dye used. So, here's the reaction itself. I take 100 milligrams of dinitrophenyl oxalate, add 10 to 15 milliliters of ethyl acetate. It doesn't dissolve completely, which is normal. It's not supposed to. Then, I add a very small amount, literally a tiny bit on the tip of a spatula, of the fluorescent dye Rhodamine 6G. After this, I turn off the lights and add a couple of milliliters of 30% hydrogen peroxide, and the reaction begins. The luminescence is very bright. You can even see that the brightness is higher than that of a surface illuminated by the sun. I tried this reaction with another dye, Rhodamine B. About 8 years ago, I did this same reaction with 15 grams of dinitrophenyl oxalate. It was epic. The luminescence with Rhodamine B was red, but the brightness was much lower. Next, I'll compare it with luminol, another very common chemiluminescent reagent. I conducted the luminol reaction not in complete darkness but under room lighting so as not to blind the camera. I used 200 milligrams of luminol, and this is how luminol glows, not very bright and for a very short time. And here under the same lighting is 100 milligrams of dinitrophenyl oxalate. Dinitrophenyl oxalate glows much brighter and for a longer time. After 20 seconds, it still glows pretty bright. After 35 seconds, I turned off the light because the glow is no more visible. 30 seconds later, reaction is mostly finished. For some time I was bothered by the question, what happens if you don't add the fluorescent dye to the reaction? Will we see white light or will the light be released as ultraviolet? The answer is no, we won't see any light, not even ultraviolet in that case. I even conducted an experiment. I took dinitrophenyl oxalate in ethyl acetate and added hydrogen peroxide. Absolutely nothing happens, but you only need to add a little bit of fluorescent dye to the solution and the mixture starts to glow. So why don't we see light if we don't add the dye? The thing is, if the intermediate product, oxatenedione, doesn't find a fluorescent dye to transfer its energy to, it will still decompose sooner or later, releasing the excess energy as heat. We won't see any light in this process. All the reaction's energy will be converted into heat. To my Ukrainian subscribers, I offer to send a kit for a small fee, containing 1 gram of dinitrophenyl oxalate and a small amount of the fluorescent dye Rhodamine 6G for a bright yellow glow. Unfortunately, I cannot offer the same to my English-speaking subscribers, at least not yet. This is primarily because I don't know how to send such items abroad. If you're interested in purchasing 1 to 2 grams of dinitrophenyl oxalate and a fluorescent dye, please email me and I will try to ship them to you. You can find my email in the video description. If the delivery is successful, I will list this kit in my shop on Buy Me a Coffee. The link will be in the description. I want to remind you that for all the reactions in this video, I used about 100 milligrams of dinitrophenyl oxalate, so 1 gram will be enough for 10 such demonstrations. Dinitrophenyl oxalate and the dye are perfectly legal substances, and they are not harmful unless, of course, you plan to eat them or cover yourself in them. Don't do that. However, there is one danger here, and that's the dye itself. It's very potent, stains everything it touches, and is very difficult to wash off. Handle the dye carefully and everything will be fine. To neutralize the dye after the reaction, you can pour an excess of bleach into the reaction mixture and wait until the red color of the fluorescent dye disappears. After that, the mixture can be safely poured down the drain. That's all for today. In one of my next videos, I'll show you how I synthesize dinitrophenyl oxalate.